Hello viewers, welcome back to live coding a Risc-V emulator in C#. Now, if you watched last episode, you might be wondering, so where's all the Risc-V content? And I promise you there will be Risc-V specific content coming up, but first we have to take care of the preliminaries. So let's go and revisit our program from last time. And as we can see, it was divided roughly into two parts. A first part here, which defines the program to be assembled and then evaluated, and then the piece that actually evaluates the code. And I thought before we get involved into any more coding, we will start by refactoring the existing code so that it's a little tidier. So we are working on an emulator, so perhaps it's a good time now to create the actual emulator class in which the emulation code will reside. So let's start by creating a new class. And let's call it emulator. And so we're introducing a new namespace, rvfun, and our class. And to start with, it will take a program in its constructor, which is the list of instructions that we created last time. Let's hang on to that. And then we're going to move over a method. This for loop here is going to become a new method called exec. And it will do the same as before. It will spin on the instructions, executing each and every one. And then this method, exec, will also move out into the emulator, and we'll make it a private method. So notice now that we're getting a bunch of errors because this emulator has no registers yet. So let's move the registers into the emulator. And we'll create them in the constructor. Alright, still have our registers, and now we have to, well, in order to print the registers, we're going to have to expose the registers. So let's just add a method on the evaluator, and we haven't created an instance of an evaluator yet, so let's do that first. Or emulator. Pass it in the program, and then what we want to be able to do is say emulator.registers, and then let's expose that as a property. All right. Shall we try building this? Just making sure that everything is still compiling. It is probably not going to compile because we have all these constants. We need to move them into a separate file. Let's call those mnemonics. And let's add a new file. and then paste them all in there. And let's make them public. And then back in our emulator, we'll import that like so. Okay, we're getting an interesting error message here. Cannot use... They are constant. Oh well. Let's switch this to a enumeration then. We can do that too. Watch me struggle against the compiler. There we go. Now we should be all right. Still not happy. I guess we'll just have to do it this way. Oh, I think I know what the problem is. We have methods, top level methods named these things, so let's go back here and see. No, that's not the problem. Interesting. Well, I guess we'll have to just keep on badgering through here. Let's change the enumeration back to a constant. Actually, let's just undo this buffer. This should work. So, why are we having so much trouble? Cannot use... That's very strange. Let's go back to the program and how very strange. And suddenly it works. Not sure what was going on there, but I finally got the compiler to submit. Okay, so we now have moved everything into the emulator except for this function, which is of course the assembler. Maybe we should make that another class. Let's go ahead and do that. So we'll create a new file, and we'll call it assembler, and it will also be in the RVFun namespace. And what this will do is it will create a list of instructions. And then we'll expose a method called assemble, which will take, we'll just grab it out of this file. It's over here. And we'll put it back into the main file like so. Make that a public method. And then let's make sure we have this field. Beautiful. And then at the end we want to get to the program. So we'll expose a method. Let's call it list. This will just return the instructions. Like so. And now we'll need to create an assembler. And then all these calls need to be replaced with assembler.asm. So let's see. Let's replace that one. There we go. And then we'll need to grab the program that we resulted. Okay, great. Finally, let's move the instruction class into its own file. Like so. Now let's try building this. Recall that the program was computing the value 0 before, so if all this refactoring went well, then we should still be printing 0. And hopefully no crashes. So let's take a look. Still returning 0. Wonderful. So now that we've refactored our program, we can take a look and see what happens. We create an assembler, we assemble a bunch of instructions, we create an emulator, and then, oh, we never actually ran the emulator. So no wonder the result is 0. Maybe we should change the program to actually return minus 1, because here we're lucky, but we didn't actually run the emulator. We have to actually emulate the program. So I changed this constant from -2 to -1 to -2. This should result in the value -1 in that register 6. There you go. Okay. So finally everything's in a stable point. So we've been dealing with very small programs so far. The programs can play around with the values in the registers. We can add and multiply them. But in a real program, in the real world, we will have large amounts of data. Much more than 32 registers will be able to fit. So we need to introduce the notion of memory, random access memory, to this emulator so that it can access copious amounts of memory, megabytes if necessary. And in order to do so, there are some few things we need to discuss. Now, I'm sure you're familiar with regular bytes in today's in parlance, a byte is 8 bits of data, an octet if you're a francophone. And that's all fine and dandy if the number of objects or different values of objects that you want to store amount to 256. So if I have numbers from 0 to 255, I can store them in a byte. But as soon as I have numbers that are larger than 255, I run into a problem because they will not fit into a byte. They will fit into multiple bytes, but I am now facing a problem. You see, if I have a very large number, like say the following number, which I'm writing in hexadecimal right now, this very large number will not fit into a byte. I can divide it up into bytes though. I can say, well, first take 0, 1, then 2, 3, then 4, 5, and then 6, 7, and store them in memory in that order. So first store 0, 1, the big end of the number, then 2, 3, then 4, 5, and then 6, 7. And I could also say, well, let's start at the little end. Let's start with the 67 part first, then 4, 5, then 2, 3, and then 0, 1. And in practice, both methods are used on real architectures. This first method is called the big endian storage order, where you store the most significant part of the number first, so the higher part of the most significant part, and then the other method, the least significant part, is stored first, and that's called the little endian method. Now, there's no intrinsic better or worse method of storing these. It really depends on your application. Different architectures in the past have chosen different endianness. For instance, the Motorola 68K that was used in the original Macintosh and the Amiga, it uses a big endian storage layout. And so did IBM when they created the IBM 360 back in the 60s. Now, in contrast, the Intel x86 family and the ARM processors all are big endian, or little endian, sorry, and famously so. And this has resulted in some ridiculous flame wars where people try to claim that one of them is better than the other. It turns out that in the end, they're both just as good, but you have to pick one and be consistent. Now, why am I bringing up this in such long detail? Well, it turns out that when you're programming in assembler, knowing which endianness your CPU is incredibly important, because you are the one who is actually writing and storing these values into memory, and so you have to be familiar with how they are stored. When you're programming in a higher level language, you can usually afford not to worry about these sorts of things, but when you are down at the assembly language level and you're worrying about individual bytes and bits, then knowing your endianness is important. Now, it turns out that Risc-V, the instruction set architecture, was initially defined as little endian, but after some comments from the public, they've changed it so that the architecture can be either big or little endian. However, the standard mode that I'm going to be implementing is the little endian mode, which means that we'll be writing the least significant pieces of our values first in memory. So let's implement memory. We have to create a memory class that implements our memory, and it will expose methods that allow us to read and write from that memory. So I'll go to my project and add another class. Let's call it memory. Maybe even the proper file extension. And it will be in the RVFun namespace. Now, our initial cut of the memory class will take a chunk of memory like this, and we will hang on to that. And then we'll add a method for reading a byte. And to read a byte, you have to provide an address, the location of the byte, and then we'll just return the value. And conversely, when we want to write a byte, we will write it like so. All right. But now we want to write a 32-bit word, and so this is where our endiness comes into play. We want to write the bytes so that the least significant bytes are written first. And conversely, when we're reading, we want to read the bytes so that the least significant byte is read first. Let's start with read word. So we'll create a read little endian word. And when I say word in the context of Risc-V, it means 32 bits, but on an x86, a word is a 16-bit quantity, so therefore I'm actually adding explicitly the word size here so that it's clear what exactly is the size of the entity that I'm reading. We're going to specify an address, and then what we're going to do is we are going to read the bytes one by one and then combine them. So the first byte, B0, is going to be this, and then like so, and then the third byte, and then the final fourth byte. So here are our bytes. Now we have to combine them correctly. So what we do is we say return B0 plus B1 times 256 plus B2 times 65,536 plus B3 times 256 times 65,536. So by running this, we will take the bytes, and then the first byte that we read will be the least significant one, and the successive bytes will be more and more significant. Now, in the converse direction, when we write this thing, we will first isolate the bytes out of the value. So we'll say var b3 equals value divided by 256 times 65,536, and then we're going to cast that into a byte like so, and then B2 is going to be the value divided by 65,536. Oh, hold on a second. Order of parentheses is important here. Then var B1 is going to be the byte cast of value divided by 256, and finally B0 is the byte of value. And now we need to write them out in the correct order. So we'll say this dot bytes at address equals B0, and then plus 1 B1 plus 2 B2 plus 3 B3. All right. So now we should test this to make sure that read and write word are working as expected. So let's go to our program here. We'll skip the emulation for now, and we'll need to create a memory. create a memory of 1024 bytes. Nice and small. And then let's use the address 0 hex 400. No, that's too much. 200. And in there, we're going to store a bunch of bytes. So memory.writeByte adder. And in that address, we're going to write the word 78. And I'm going to use hexadecimal notation here. In the next byte in memory, we're going to write 56. 34. And finally, 12. So, if we write these bytes in this order, we're getting the number 1, 2, 3, 4, 5, 6, 7, 8 stored starting at address 200. So now if we execute read word at that same address, we're expecting the number 1, 2, 3, 4, 5, 6, 7, 8 to come back out. So let's see if that is truly the case. And we'll write out the result in hexadecimal. Let's comment out this code since it's not the one being tested right now. Let's run our program and see what happens. And there it is, 1, 2, 3, 4, 5, 6, 7, 8. So it looks like the read word is working correctly. And of course, to be super rigorous, we should also test the write word. So let's do that. Mem read or write le word 32 at the address 0, 1, 2, 3, 4, 5, 6, 7, 8. And so now we're expecting the bytes to appear in the following order. So let's write memory read byte at adder. And then adder plus 1, adder plus 2, adder plus 3. So now the idea is that we'll be reading those same bytes that we wrote at that address, and because we're writing in little endian mode, we expect the little n to be written in the first byte, then the 5, 6 in the second byte, 3, 4 in the third byte, and the final 1, 2 in the fourth byte. So we should see 7, 8, 5, 6, 3, 4, and 1, 2 appear on our screen. So let's verify that. And indeed, they appear in the order we expected. So we're satisfied that we have now implemented write and read word correctly. Great. So now we can start implementing the instructions that allow us to write programs that read and write memory. So let's start by adding a memory parameter to our emulator, because the emulator needs access to memory. So let's bring this code back. And the code will now pass into the emulator not only the program to emulate, but also some memory. Like that. And then we change the constructor of the emulator so that it has access to that memory. There we go. Let's now define a new opcode. One to read a byte and one to write a byte. load byte will read a byte from memory, and its counterpart store byte will store a byte to memory. And since we're here, we might as well add two more. One, load word, and remember that word on the Risc-V is a 32-bit value, so this load word instruction that we're defining will be reading a 32-bit value. And then store word will conversely store a 32-bit value in little endian order into memory. Great. So how do we define these instructions? Well, recall that we have this big switch statement that performs all of our instructions, so all we need to do is add a case for load byte. So what does a load byte instruction do? Well, it needs an address. It needs to be told where to go fetch, what location in memory do we want to fetch. And so that is going to be one of the input parameters of the instruction. Let's put that in source 1. So and then it's very, very common on CPUs that you usually have the address of an object in a register, and you want to access the different fields of that object, which usually are located very close to the pointer to the object itself. And so what you want to do is be able to access memory locations that are small offsets based off of the object address itself. And the way that we're going to implement this is by allowing you to supply a small offset. So what this will do is it will read the contents of the register specified by the field source 1 and add a small offset which is stored in src2. And of course, if src2 is 0, then we're just going to read directly from the pointer or the memory addressed by the pointer. And the result of this addition then is something traditionally called an effective address. So this is the effective address. This is the location in memory that we're going to be reading our byte from. And so what we do now is we say mem read byte. And we pass in the effective address that we want to read from, and out comes a byte. Now, here's an interesting subtle issue that you have to be aware of, because remember, we're assembly language programmers now, and everything low level has to be taken into account. A byte is an 8-bit quantity, but we want to read this out and put it into our register where other instructions can later consume the byte and do things with it. So we have to convert the byte from its 8-bit size, which is now, to something that will fit in one of the registers. And the way that the Risc-V instruction set architecture does this is by, and now I am running into a blank. I think it's doing it by sign extending the byte. So what that means is that if the highest bit of that byte is set, then the resulting sign extension will convert that into an integer, which is also signed. So we have to convert this byte into a signed byte. This will tell the C# compiler to treat the byte that's coming out of the read byte call as a signed byte. And then we'll store that into the register inster dest. And what this will do is then the C# compiler will convert the signed byte to a signed integer and then store it into that location, into that registry slot. Let's write the word as well. In the case of loading a word, we want to compute the effective address just like before. But this time, what we're going to do is we are going to read it using the mem.read leword32. method, and so now that comes out as an integer, and so we don't have to worry about any sign extensions. There we go. And now for store byte, what we want to do is again compute an effective address, location where we want to store this byte, and what we do now is we say memory write byte, and we take the effective address, and then we take the value that is stored in this register, and this time, because that is a integer, we have to just strip it down to a byte, and then we do that by using one of our casts like that. So this will take the least significant 8 bits of that instruction and store them in the memory. And then finally, we're going to do the same thing again, but this time we're going to be storing a word, a 32-bit word. So it will do memory write le word 32 to the effective address, the value that's stored in Notice how in the store instructions we are using the value, the register index in the destination slot to indicate the value that we're reading from. This is abusing notation a little bit. It's slightly confusing because normally the destination is the index of the register that we will be updating or changing in the instruction, and here we're reading from it, not writing to it. This is the only time that we diverge from this, and the reason why I'm doing it this way is because that's how the Risc-V instruction set architecture does it. So now that we have these 4 new instructions, we can now start writing some code with them. So let's go back to our main program, and we're going to throw away our trusty initial code, and we'll write a little program that reads some bytes and reads them back out again. So, for instance, let's write store byte. Well, before we even can do store byte, we have to initialize one of our registers with a value so that we can write to that area in memory. So let's do the add I to register 4. We're going to take register 0. Remember that register 0 is always set to 0, and then we're going to add a small offset to it, like the hexadecimal 10. So what this will do is it will take the contents of register 0, which is 0, add the hexadecimal 10 to it, or 16 if you want to think in decimal, and then store the result in register 4. So register 4 now has 0x110 in it. So now that we have the register 4 set up properly, we can now start writing using that register. So we'll store a byte, and what byte shall we store? Well, we also need to put that in a register. So let's do this. Let's put into register 5 the value 1. So again, add immediate takes the register value of register 0, which is always 0. We add a 1 to it. That gives us a 1. And remember, this is an immediate add, so that's why we're adding a 1 and not the contents of register 1. And the result is now stored in register 5. So initially, register 5 contains the value 1. So now what we'll do is we say take the contents of register 5 and store them using the pointer whose value is in register 4 and at offset 0 from that pointer. And then what we can do is we can use the add immediate instruction to add 1 to the register value in register 5. So here I'm saying add the immediate value 1 to the contents of the register 5, which initially is 1. It's now going to be, the sum is going to be 2, and then we store that sum into register 5. And then we can store that into the memory location that's 1 byte past the address that is stored in register 4. So this will write the number 2 into the memory location after, or the memory location 1 hexadecimal. And let's repeat this pattern 2 more times. And let's increment this after each add. So what this should be doing is writing the byte 1 to address 10, then the byte 2 to address 11, byte 3 to address 12, and finally the byte 4 to address 13. So after running all of these, we should now be able to read the value in with a load word. So let's do that. We're going to load the word. We're going to put the result in register 6, and we're going to use register 4, which is still pointing to the first byte of all those bytes that we just wrote. And we ask, please start at offset 0 from that pointer value. So that should read in these bytes that we wrote in little endian order. And then at the end, once we run our program, we should be able to dump the result, which is in register 6, to the screen. And it should be something like 4030201. So let's see if I got everything right. Of course, it helps if we write the result in hexadecimal. So let's do that. And there we have it, 4030201. So we've now expanded our little emulator so that it can read and write bytes and words from memory. Great steps, but the keen-eyed among you have noticed that we're still not able to do any loops, any kind of repetition, and we cannot do any sort of conditional execution. That is, look at a value and deciding whether or not to do something based on on that value. And in order to do so, we need to implement jumps, conditional jumps, and that will be the topic of the next session. Thanks for watching.